Hey, in this video, we're going to be talking about rotational dynamics. So we're going to put it all together using Newton's second law to use the net torque equals I alpha. And we're going to be applying that same problem solving step process that we did in Unit 2. We're now going to be applying it into the rotational form here. All right, so now we want to put it together for rotational dynamics and all the steps we're going to go here. And it's ultimately doing this net torque equals I alpha. Okay, so first step, we're going to draw the free body diagram and place the forces where they're acting. Gravity acts at the center of mass. All other forces act where it makes physical contact with the object. We're going to handle some pivots, axes, and handles. Technically, one of the tricky things about hinges, if there's things that are rotating, it's still a normal force. However, because it's circular, the normal direction can be any direction. So pixel, and we'll go through some examples in there. We then want to identify the axis of rotation. If we're in rotational statics, that is, there's no angular acceleration, you can pick any point that's convenient to be the axis of rotation. When the angular acceleration is not zero, which we're going to talk about today, we're going to pick the point at which the object is spinning around dynamics. For rolling objects, pick the center of mass of the object. And we'll get into that. We're going to assign positive and negative directions to clockwise and counterclockwise. So we're going to assign our directions. For each force, compute the torque. Apply net torque equals I alpha. You may need to compute the rotational inertia. Okay. If the angular acceleration is non-zero, you may need to calculate the rotational inertia there. And if needed, apply F net equals ma. Seems like a lot of steps, but as you can see, we've been building up to this point. And so let's apply those problem-solving steps now. So example, I have a uniform rod of mass m, length L, and a rotational inertia 1/3 ml squared around the end is held vertically by two strings of negligible mass. Immediately after the string is cut, what is the linear acceleration of the free end? We want to know what the acceleration here is equal to. Not the acceleration of the center of mass. That would be different. So what are we going to do? Step one, we're going to draw a positional free body diagram. Now this road is cut, so we have mg acting at the center of mass of the object, and then we have a tension here touching it. There's nothing else touching it, so that's the entire free body diagram. Then what's our strategy to figure out this part is we're going to use net torque equals I alpha, so we got to assign positive or identify our axis of rotation. Because I don't need to know the tension, we're just going to make that our axis of rotation, and that's also because the rotational inertia was given around the end. Okay, so that's our axis of rotation, and then we're going to assign our positive directions. We'll make clockwise negative, counterclockwise positive, and then we're going to use net torque equals I alpha at this point. This will give us the angular acceleration, which we can then use to convert to the linear acceleration. And we'll remind you from kinematics how we have to do that. So now the tension's not going to exert a torque. mg is going to exert a clockwise torque. Okay, the clockwise torque is going to be negative, so it's negative. And the distance from there to there is L over 2. It's already at a right angle. Times mg is equal to ml squared times alpha, like that. I times alpha there. The m's cancel. One of the l's cancels. And so you get the angular acceleration is going to be negative 3/2 g over L. Now the negative just indicates that it's going in the clockwise direction, right? Now, what about the linear acceleration at the end? Remember when things are spinning, we had those tangential accelerations. How they're connected is that we had the distance was equal to r times the angular displacement. Velocity at the linear velocity was r times the angular velocity, and the linear acceleration is r times the angular acceleration here. So the linear acceleration is going to be the distance from the axis of rotation. If I want at the end here, that distance is going to be L. And then we're going to multiply by the angular acceleration, negative 3/2 g over L. The L's cancel, and you get it's negative 3/2 g. And as you can see, the negative just indicated this is down. And there's some consistency with the down and clockwise being the negative directions. Okay. How about from the middle of the stick? Well, the angular acceleration is still the same. It's just that the r is going to be the distance. If I want at the center of the stick, then it's going to be r, which is L over 2 times the angular acceleration, negative 3/2 g over L. L's cancel. This becomes negative 3/4 g. Okay, cool. Let's do another problem here. So we have a horizontal uniform rod shown. 2 kilograms here, has a 0.5 kilograms at the end, length of 0.6 meters. So all of this is just describing this picture here. Left end of the rod is attached to a vertical support by a frictionless hinge that allows the rod to swing up or down. The right end of the rod is supported by a cord that makes the angle 30 degrees with the rod. Okay, that's this part here. Spring scale measures the tension in the cord. On the diagram, draw and label vector. So we're to represent all the forces. So we're drawing a positional free body diagram. We're gonna have the 2G here at the center of mass of it. And we're gonna have a rope here, or you can just think of it, that weight is attached there at 0.5 G, the point there. And then let's see. Yeah, we're going to do the rod and the block. Yeah, I was just reading the other parts of the question. What else is touching it? We have a tension force this way at the end at this contact point. And then the hinge force. Now, here's the thing. If it's just hanging out here, the hinge force is a normal force in any direction because it's a circle. So we're going to think about, remember, the normal force is perpendicular to the surface. But if you zoom in on a hinge, it's a circle. So normal can be pretty much any direction because a hinge, one of the reasons that circle is that that normal force can be in any direction perpendicular to the surface. So it can be any direction. And we're just going to say there has to be a rightward component to cancel out the tension, which is kind of like pushing it to the left. So we'll say it's up and to the right, but we don't know any angle or anything like that about it. Okay, that's all that's touching it. So we're done with our free body diagram. Part B, calculate the reading on the scale. Now we want to identify axis of rotation. In this case, the hinge force, we're going to put the axis of rotation right there because we don't want to calculate the hinge force. I just want to calculate what the tension is. Okay, and so we'll make counterclockwise the positive direction, and then we'll do net torque equals I alpha. Now in this case, the rotational around the center is 1/2 ml squared, where m is the rod and L is the length. In this case, I don't need the rotational inertia because we know the angular acceleration is going to be 0. So we don't need to do this part yet, but for part C and D, when the angular acceleration is non-zero, I may need to know this, because if this part's 0, it doesn't matter what the I is. Okay, so the hinge force doesn't exert a torque. The 2G, the R vector looks like this. That's 0.3 meters, half the distance of the rod. And that's a negative torque because pulling down there would cause the beam to rotate clockwise. So that's going to be negative 0.3 times 2G. And I'm just going to use G of 10 and make that 20. Then we're going to do the 0.5 G. That's also going to be a negative torque. It's going to be 0.6 because the distance from here to here is 0.6. It's already at a right angle. And then times 5. And then finally, we're going to have a positive torque from the tension. But we got to think about the component of the tension that is perpendicular to the R vector. That's going to be, this is 30 degrees, T sine 30 degrees. Right? And so this is going to be positive 0.6 times T sine 30 degrees. And that's going to equal 0. Okay? That's the net torque is going to be 0. And then we're just going to solve for this. So this is going to be this is minus 6 minus 3. So this is minus 9. So move it to the other side. So 0.6 T and sine of 30 degrees is 1/2 is equal to 9. So the T is going to be 18 divided by 0.6. Which is going to be 30 newtons here. Okay, now we have the rotational inertia around the end is 1/12 ml squared, where m is the mass of the rod and L is the length. Calculate the rotational inertia of the rod block system about the hinge. So now we're talking about this whole system here. We're going to do the rod, which is rotating around the end, not rotating around the center of mass. This is about the center. So the rotational inertia of the rod around the end, because we're rotating around this axis right here, it's around the end, we have to do parallel axis theorem. So that's going to be 1/2 ml squared plus how far you shifted it. Here's the center of mass of the rod. You shifted it a distance 0.3 meters. So that's going to be m times 0.3 squared. And so let's just plug in the numbers here. We have the mass of the rod is 2. The L is 0.6 squared. The mass of the rod is 2 plus 0.3 squared. So this is that parallel axis theorem. So that's going to give us a number. Then of the block, right, this thing here, there's no, ignore the distance. Well, the axis is here. The axis is, even though there might be a vertical distance, that distance R, we don't know. So let's just assume that it's really, really small. Otherwise, we technically wouldn't be able to solve it. So then the distance from here to here is 0.6. So that's just 0.6. squared, it's mr squared times 0.5. And so we're going to add those two together. That will be the rotational inertia of the entire thing. So 112 times 2 times 0.6 squared plus 2 times 0.3 squared plus 0.6 squared times 0.5. I get the total. If I add these two together, I'm going to get 0.51 kilogram meter squared. Okay. So then if the cord that supports the rod is cut near the end, so we've now cut it, okay, so this tension rod now goes away. What's the initial angular acceleration of the rod block system? So now we just do net torque equals I alpha. We know the I. The net torque is just going to be this portion of it because the rope's going to be cut. So it's going to be negative 0.3 times 20 minus 0.6 times 5 is going to equal our rotational inertia times alpha, and then you can just solve for alpha. So this is going to be minus 9 divided by that number, and I'm going to get alpha as negative 1.76 radians per second squared. Okay, and then it's only negative because we said clockwise was negative, and that's the way it's going to accelerate. Okay, so you can see it's a lot of steps, but it's built up to this point, right? All the problem-solving steps have led us up to here, to this point, in doing all of this. Okay, now I want to talk about something real quick about pulleys, because a lot of times in Unit 2, you would have seen a lot of problems say, like, assuming a massless frictionless pulley. Let's talk about non-ideal pulleys now. We've always assumed that pulleys were massless, had negligible friction, and this implied the tension was uniform throughout the rope. Because if I had a pulley, let's say I had something like this, okay, and we had like a normal table and a block here and a block here, and we said that the tension here, if you think about the free body diagram of the pulley or the torque that's acting on the pulley, like there was a tension here and there's a tension here. And we said if it was really easy to spin, you don't need much of a torque. There's not a net torque necessary to cause something to rotate, because if it's massless, then the I is close to 0. And so when I do net torque equals I alpha, well, if this is about 0, then I don't need any torque to cause any angular acceleration, because it's just like I just need an infinitesimally tiny amount of torque to cause it. However, if we have to handle the math, if this is not 0, then we need a net torque on the pulley in order to cause it to rotate. And if you think about it, if the tension were the same, okay, and we're doing this as our axis of rotation, you're not going to have a net torque, because one torque here is going to be R times T, the other torque here is going to be R times T, right? But one's clockwise, one's counterclockwise, the net torque will be 0. So these two tensions are not equal anymore. So T1, we now call it T1, T2. T1 is not equal to T2 if we have a non-ideal pulley, or at least like there's some mass to it that's going to require a net torque to cause an angular acceleration. So now we consider that a non-zero net torque is necessary to cause a pulley to rotate. So let's look at a scenario here where we have this case, okay? The cart shown below moves across the tabletop as the block falls. What is the acceleration of the cart? Neglect friction and assume the following data. This is here. Note the tension is not uniform with the rope now. Okay, so let's draw our free body diagram, but we're adding in a new step. We got to add in a free body diagram of the pulley itself, okay? So here, just like we did Unit 2, this is going to be M1G, and we're going to call this a T1. This is going to be M2G. You're going to have a normal force here. There's no friction, and then you're going to have T2 here. Now we have to do the free body diagram of this guy. You got a T1 acting down here. You got a T2 acting down here. You got gravity acting at the center of mass, right? And then you also have some force from the hinge that's holding it in place. Because if these were the only forces, it would just fall down and go to the left, right? Like so. But there's a hinge force acting at the axle to keep the center of mass from moving, right? That's why it can just rotate, but the center of mass is just stuck there, right, for that pulley. Now you want to assign directions, okay? Before we do the F net equals ma, we got to know which way everything is accelerated. This thing is accelerating down. This is accelerating to the right, and then this thing has an angular acceleration associated with it. And I always do that because then we can make those directions the positive directions. You want consistency. Remember, we wanted consistency between our defined acceleration directions when we did it with the blocks before. Now you want to be consistent here. So we're going to make those the positive directions for the accelerations of the blocks and the angular acceleration. You want consistency, otherwise you might get some sign errors if you kind of mess it up. For each block now, for the M2 block, we're going to do F net equals MA, and we only need to handle the X direction because we just care about the acceleration. So that's going to be T2 is going to be M2 times A. For block M1, it's accelerating downward. So when we do F net equals MA, it's going to be M1G is going down, T1's going up, and that's equal to M1 times A. And before, we had the tensions uniform when we did unit 2, so we could just cancel each other out. But now we got to do the pulley. Now, we're going to use net torque equals I alpha. Why? Because the acceleration of this, if I do F net equals MA, that should be 0. Because the net force, because the center of mass is not accelerating. But it is rotating, right? And that's connected to these guys over here. So, what's our axis of rotation? Well, it's right in the center here. Now, that means the axial force and the gravity on the pulley don't exert a torque because the R is 0. So, only T1 and T2 are exerting a torque. Okay, and so the distance is R, so that the T1 is going to do a positive torque because that would cause the pulley to, if I pull down on the right side of the pulley, it would rotate clockwise. The T2 is going to be a negative torque because if I pull in this direction, the pulley would rotate counterclockwise, and that's the negative direction, and that equals I times alpha. Now, one thing to keep in mind, how are these related? Well, at the end here, the linear acceleration at the end here matches that, the A equals alpha R. Okay, because the linear acceleration, the speed that the rope is unwinding is the speed is related to the speed that it's rotating is related to how fast this thing is falling. So they're all connected, and so then you can replace the alpha with A over R, and then we could divide the R. We get T1 minus T2 is equal to I A over R squared if you factor out the R and divide it. So now we have these sets of equations, but now let's replace all the things that we know because we just want to know the acceleration. So we're going to replace the T1. Okay, so the T1 here is going to be M1G minus M1A. So here it's going to be M1G minus M1A minus T2, which is M2A, and that's equal to IA over R squared. Now we just want to group all the A's together, so we get M1G is equal to I over R squared times A plus M1A plus M2A. We can now factor out an A, right? I over R squared plus M1 plus M2 is equal to M1G, and then divide the thing over. So the acceleration is M1G over I over R squared plus M1 plus M2. And I'm not going to plug in the numbers for that. I think the most important part is you're able to set that up. Okay, and solve it. You can plug in those numbers you want. That's the whole process. Feels like a lot. I know it can feel a little bit challenging, but we want to be systematic. Go through each of those steps. Make sure you're able to do all of those steps. If you found this video helpful, come check out our school community. It's got an amazing bunch of features. It's got extra videos, corrected videos, better than the ones that I have errors on YouTube. It's got multiple choice free response questions. I hold live Q&A sessions and go through more problems and I answer students' questions, help with schoolwork, all kinds of things. If you want to check it out, look in the description below or check out the website and find us in the school community. You get a 7-day free trial to give it a shot, just to check it out, see what it's like, come join some calls, and honestly, come learn AP Physics 1 even faster with us.